Okay, welcome to class. Okay, while you're getting your clickers ready for the reading quiz, I'm just going to go very briefly over the very last thing that we didn't get to in last class. And that's basically, we talked about failure, we talked about crack growth, we talked about static fatigue, where the crack grows even though you don't think it's cycling, we talked about thermal stresses, and at the very end we talked about creep, which is, okay, you apply a load and it actually starts to deform, but it takes a long time for it to happen. The last thing that we didn't get to was how do we accelerate our problems, right? Our failure problems. If, for example, the roof is going to, after 20 years, it's going to bend and break, how could we accelerate that testing so that we could design around it, right? So accelerated testing is a big deal. One way you can do it is you can do stress rupture curves, because both heat and stress will typically speed up the process of failure. So stress rupture curves look something like this, right? Here's the stress plotted on the y-axis as a function of rupture time, right? So at a given stress, whatever this is, say at this value right here, you can plot that out and see where it intersects different temperatures, right? Where temperature 3 must be your highest temperature because it lasts the shortest amount of time. Temperature 2 lasts much longer, right? So you could generate these so-called stress rupture curves for lots and lots of different temperatures, right? And that's one way to do it. But a better way, because what if your temperature is between, say, temperature 2 and temperature 3? A better way to do this is with something called the Larsen-Miller parameter. And you've seen this on the homework, so let me just recap it. The Larsen-Miller parameter is a type of stress rupture curve where you're plotting the stress at which something's going to fail as a function of the Larsen-Miller parameter. The Larsen-Miller parameter is typically something like this. It's the temperature divided by 1,000. It doesn't have to be this exact form. It usually looks something like this. Multiplied by a plus b natural log t. A and b are your constants for your given material, right? Or class of materials. This is a bunch of different steel alloys, right? T is time that it'll survive in hours. So let's do an example of this. If you had this figure, this is showing you the stress versus Larsen-Miller parameter for some sort of iron alloy, right? If the question was as follows, what is the maximum stress in PSI for this iron chain if it's going to be used in a furnace for 5 years at 600 Celsius? The way you go about solving this problem, and I've already worked it out for the sake of time today. First, you figure out how many hours are in 5 years, right? You convert that to hours, and you've got now your time. Now that you have your time, you're going to plug this into your Larsen-Miller parameter equation, and that's given here along the x-axis, right? So we say, okay, we know temperature is 600 Celsius, turn that into Kelvin, and now you can plug those into your Larsen-Miller parameter. So all I've done, yeah.
In the homework, we have, I have a question in the homework that sometimes, well, for example, in the homework we have log of something. Is that just supposed to be ln, natural log? Or?
In my class, if it's ever supposed to be log base 10, I'll write log with the little subscript 10 next to it. So on the homework, I don't recall what is written. Does it say log? Does it not say base 10? The PDF problem, does anybody have it here handy? I took that from a website I found, that example, so I don't know what they intended it to be. Somebody have the homework here? So let's just have you do log base 10. If they wrote out log, then let's assume it's log base 10. I'll give you credit. If you worked it out natural log, I'll give you credit if you did it either way. But whenever I write a question, I'll make sure to try and put, first off, I almost never use log base 10. I'll use natural log. Okay? But if you worked out either way, we'll give you credit this time, because I know it's due on Wednesday. Okay, so your Larsen-Miller parameter equation, when you plug these things in, right, you're just going to plug them exactly into this equation that you saw here, right? When you do so, you figure out that the Larsen-Miller parameter for this alloy at that temperature and that time comes out to be 38.7. So all you have to do is figure out where that is on your plot. 38.7 is right here. You draw a line up, see where it intersects the line given for that alloy, and figure out what stress it would take for it to survive under those conditions. So this is it's a convenient way to show lots and lots of accelerated lifetime testing on one plot. That's why we use these Larsen-Miller parameters. If you're going to buy an alloy from someone, and if they report anything about its lifetime and accelerated testing, it'll be a Larsen-Miller parameter type of thing that they'll show. Any questions on this before we move on? This is the last thing we didn't get to. Yeah, Rosa?
So when you go over, you say that was like 1900
Yeah.
Is that the maximum stress that it can take at all throughout its like 20 lifespan?
That means if you want it to survive 5 years at that temperature, and you leave it at that stress the whole time, at 5 years it's going to fail. Now, what do we mean it's going to fail? Again, this should be plotted as a function of probability of failure. That's probably like half the time it's going to fail. So to make it more accurate, you'd want to show 1%, 25%, 50% failure rates, but that's not shown on these typically. And obviously, because that's the point at which it fails, when you design around it, you're going to design your applied stress to be lower than that still, because you don't want things to fail, right? You want to design around failure. Okay, let's shift gears then. We're going to talk about Chapter 3, and a quick announcement. Last class, a bunch of people showed me that their app wouldn't let them put answers in. Not a bunch, probably 3 or 4 people said that they couldn't actually, there was no decimal place, or they couldn't type the number 9 for some reason. If you're having weird responseware issues, first off, make sure that I give you credit for being in class. Just let me know. If you send me an email after class, I'm always happy to give you the points for that day. But more importantly, send me what your device was that you're using it on, so I can forward that along to the people at responseware and they can get that fixed in the future. So if that happened to you. Okay, let's start with our reading quiz for today. Okay, the first question is, what crystal structure is this? Is it A, FCC, B, BCC, C, zinc blende, or D, perovskite? Okay, get your answers in. Okay, we're going to wrap it up. Panic. Okay. Okay, is it A, B, C, or D? Okay, definitely it's A, right? Let's do our next one. The hexagonal close packed, or HCP structure, and the face-centered cubic, FCC structures, have the same atomic packing factor, true or false? Okay, answers in, true or false. Okay, wrapping it up. Okay, pretty split. We'll go over this one today. Because it was so split, I'll probably make it a point on either one on that one. Okay, and then the last reading quiz question is, the coordination number for atoms in body-centered cubic is 8, 6, 4, or 2. Okay, answers in. We're wrapping it up. Okay. Okay, it is definitely 8. All right, so that said, what are we going to talk about today? We will finally be able to describe what phases are. We've been calling them these Greek letters. We've been giving them, names up till now, but we haven't really said what they are. So today we're going to start to describe what some of the simple ones are. There's actually, and this is something that we do research in my group, there are at least 10,000 unique different ways of forming crystal structures, right? I'm sure there's more, but we have identified 10,000, right? We're not going to talk about 10,000 in this class. We'll talk about maybe 5, maybe 6, right? Just the most simple, most common ones. Okay, we'll define what coordination number is. We'll introduce some of these basic ones, BCC, FCC, HCP. Importantly, we're going to establish relationships between the size of the atoms, right, involved with the ions, and the size of the lattice that comes out of it, right? So bigger atoms, bigger lattice, but can we be more quantitative about it? I'm going to define that twice, apparently. We'll be able to calculate the theoretical density of compounds, as well as the packing factor, linear density, and planar density. And we'll be able to use the cation to anion ratio to predict what type of structure forms. So basically, if you know that you have two atoms and you know the size of these two, if you take the ratio, that'll usually tell you what the structure is. And if we have time, we'll start talking about some basic ceramic structures, and maybe we'll go from there. So what have we covered so far? We talked about bonding, we've covered chemical reactions and free energy, we've talked about phase diagrams. And let's go back to phase diagrams for just 1 second to introduce concepts of structures. We know that this along this line over here is pure iron on the far left. That's pure iron. And we showed you with the iron wire demo that something happens. It switches from one phase to another. You saw the volume expansion, and so you saw that's one proof of it. Here's another proof, though. If you look at the phase diagram, look at this low temperature phase, alpha. How much carbon can fit inside of it? At maximum, the maximum solid solubility of carbon in pure iron is 0.022%, right? So a pretty small amount. However, if you go to that higher temperature phase, gamma, it can fit all the way up to 2.14 weight% carbon in it, right? So even though you're still talking about a lattice of iron, one of them can barely fit any carbon inside of it, and the other one can fit a ton of it inside of it, right? So if there's more going inside of it, the carbon is actually fitting interstitially. That means in between. Because remember, atoms can either substitute or fit interstitially. So imagine if you guys are atoms in this room, and I have extra students, and we're trying to cram them in here, we run out of seats. The next possible option is for me to start cramming them in between people, right? And carbon's a small atom, so it can fit in between people pretty well. But in one of them, it can fit over 10 times, like 100 times better, right? So why is that? We'll show you why by the end of class today. Okay, before we show you some crystal structures, let's talk about what is the basis of crystal structures. And the basis is something called periodicity. Periodicity just means something can be repeated over and over and over and over, right? So if you have a lattice is something that's repeated over and over, right? Like this lattice here is repeated over and over. So what I'd like you to do is sketch it on your piece of paper, if you've got one with a neighbor. Sketch something that looks like this, and then I want you to draw the smallest possible unit cell. A unit cell is an object that can be repeated over and over to fill all space using only translation, meaning you're not going to rotate it, you're just going to move it over. Okay? So give that a shot. Try and sketch it down on your paper. Where's our smallest unit cell? Okay, anybody want to take a guess? What is our smallest possible unit cell that can be repeated via just translation, meaning sliding up and down, left and right? Somebody said a hexagon. All right, let's draw a hexagon on here. So something like that, maybe. Can we translate that? Sure, like you could shift it down and over and you could draw another one right there. That's one possibility. Is it the smallest? Not the smallest. Yeah, what do you think, Rob?
Either a diamond or a pillow.
Yeah, a diamond, like a rhombus, like one of these. Yeah, that is our smallest. What else would you see? Oh yeah, maybe drawing it like that.
Yeah, all the same.
Yeah, same thing. Same difference, right? Now some people, are there any other guesses? Oh yeah, in the way back? Yeah, Barzin, right? Barzin suggests maybe a triangle. That usually comes up. It's not a triangle because to fill a triangle, you actually have to rotate it to get that triangle. You'd have to rotate it by 180 degrees. So a unit cell has to fill all space. Like we could fill as big of wallpaper as we wanted with that with only translation, meaning side to side, up and down, without rotations. So actually, we can rule this one out, and this one's not the smallest, so it's actually either one of those two. Okay, fair enough? So that's our unit cell, and this is with the atoms that are arranged like that. We could have arranged it differently, right? You could have had a lattice that was like this. Imagine those are all equal spaced. I was a better artist, right? Again, you could choose all sorts of lattices. You could say Well, what about a lattice like this? You could do that, but that's not your smallest. Your smallest is going to be this one. Okay? So that's your unit cell. We'll come back to unit cells in a bit. Let's now talk about some extensions of that. The first one are in the metallic structures. The metallic structures are the simplest type of structures. One of the reasons that we like metallic structures first is because they tend to be non-directional, right? Remember from when we talked about bonding, a metallic bond is one where as long as the electrons are around, they sort of all share them. Sometimes they use the sea of electrons as the words that sometimes people use to describe bonding in metals, right? Because of that, they don't need to have an electron in a specific spot as long as it's somewhere around. What tends to happen is very densely packed structures. The electrons are all around, so all the cations sort of collapse together in a very close packed structure. So let's draw our first one. Our first metal lattice that we're going to learn about is FCC, which stands for face-centered cubic. So we're going to start by drawing a cube. Right, so you've got your cube. Now the first step to drawing an FCC lattice is to recognize that the atoms are going to be on the corners first, right? So we've got our corners occupied by atoms. And then, like the name suggests, we also have face centering. So along all the faces of this, if this was like a dice along all 6 sides of the dice, you're going to put an atom right on the face, right? So you've got an atom right there, the front, the back, left, the bottom, all 6 of those sides. This is the face-centered cubic. So again, atoms are on the face centers and on the cube corners. And because this is so far just a single metal we're talking about, like pure aluminum, pure silver, pure gold, copper, all those form in this structure, all these atoms should ideally be about the same size, right? If we sketch them with a little more accuracy, they'd be the same size. Now, because it's a non-directional bonding and this thing wants to collapse as small as it can be, I've drawn it with some gaps here, but in reality, we know that there won't be any gaps. That's just the way I've drawn it. It would actually collapse until there's no gaps between the atoms, until they're touching, right? Sometimes that's called the hard sphere models. Like imagine you had a bunch of marbles and you packed them together. They're going to rest until they're touching one another. So the question is, where would they touch? In this model, if I'd drawn it correctly, where would the atoms be touching it? Maybe turn to a neighbor and take a guess where they ought to be touching. Okay, where might they be touching? Let me ask, can I pick on you, Randall? Where might they be touching at? No idea? Andrew, you want to help them out? Where might they be touching?
They're going to be on the corners, so it's kind of diagonal.
Yeah, diagonally from corner to corner. Again, if you draw these atoms along this, they're going to be touching along that direction. So let's draw our atoms in here, right? I'll try and draw these the same size as one another, right? Maybe something like that. In a face-centered cubic arrangement, they're going to be touching along what we call a face diagonal, right? It's the diagonal line that cuts the face in half, okay? They're touching there, okay? Because of that, we can introduce our next concept, which we talked about previously. It's called the lattice parameter. Remember the lattice parameter, A, is this distance along one of these cube edges. We talk about lattice parameter because it's useful. Like if you have a big unit cell, you have a big lattice parameter. If you have a small one, you have a small lattice parameter, right? So now the next question is, how do we relate lattice parameter to the size of the ions? Can you think of, and try this out, I'm going to try and write an expression that relates lattice parameter A in terms of the radius of one of these atoms, R. So with a neighbor, try and write out what should A be in terms of R. I think I figured out what that is. I need to get my laptop fixed. I think it's doing phantom touch on the screen, which is a bummer. Okay, let me ask, Allie, you want to give it a shot? Where would you start on a question like this?
45 triangle.
That's a 45-45 triangle, right? You could use Pythagorean's theorem to figure out the length of that diagonal line. So the length of that line, if the two sides are A, what's the length of the diagonal? That's just going to be root 2 times A. That's the length of our diagonal. And that's equal to how many radii? It's equal to 4 radii, right? Everybody see where this is coming from? This chapter is a lot of geometry, but it's not so tricky actually. It's pretty straightforward, right? So now you know that, you could rearrange and you say, okay, the lattice parameter then should be equal to 4 times the radii of whatever your metal ion is, divided by root 2, right? Straightforward? So again, if I gave you a radii for gold, silver, aluminum, you could predict the lattice parameter. And if you do this, it's actually pretty darn close to what the actual lattice parameter is. It's a pretty great way to estimate, okay? So let's do that.
Or divide by square root of 2.
Yeah, you could rewrite it in another way if you wanted. Like 4 is, yeah, you could rewrite it another way. I don't think it's easier, but... Okay, let's do this clicker question then. If the lattice parameter for copper is 3.601 angstroms, what is the atomic radii in angstroms? Let's make an announcement. Say, just write an expression for time 1 in terms of time 2 to the hours, and I'm just addition. Yeah, because everyone has the same problem. Okay, get your answers in another 30 seconds, we'll say. This is just a one-liner calculation. Okay, answers in. Phone a friend if you need. Okay, we're gonna end. People got their answers in. Okay, the answer is, what do people think? 1.27 is the right answer. So 90% of people got something close enough to get credit, and 10% something's off on. Okay, so again, straightforward to do this, you're just going to say that 3.601 angstroms is equal to 4 times the radius divided by square root of 2. So to solve for r, it's just going to be 3.601 angstroms times square root of 2 over 4 equals 1.27 angstroms. Okay?
Now,
next, yeah.
Why did you only keep 3 significant figures? Because when you plug it in, you get the next. You could do 4 sig figs if you wanted. That's where the 273 comes in now.
Which would give you the right answer. On these, I always accept a range of answers, and I'm pretty generous on my range.
Cool.
All right, next question is, how many atoms are there in the FCC per unit cell? And to answer this one, you need to take into account that the structure, again, drawing it is straightforward. You've got them on the corners, 8 of them on the corners, and you got 6 of them on the faces. But not all of these are completely inside the cube. So I want you to figure out how many atoms are completely inside the cube. So add up the fractions to figure out how many atoms there are per unit cell. Okay, so get your answers in. How many atoms are there per cube?
That's on the top. That's on the right.
Right side, top, bottom, on the back.
Nope. Definitely on the top, bottom, left, right, front, back, and then the 8 corners.
Yeah.
So nothing in the very center.
I know that's how it's supposed to be. But I see.
So again, just to count these, you've got the one in the back, right there, the one in the front, the left, the right, bottom, and top. And the other ones are on your corners, right? Corner, 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 corner. Okay? Okay, get answers in. We're going to end it. What do people think? How many atoms are there? Okay, the answer is 4. So 2/3 of people have got that one right. So where are we going off? Well, there's 8 atoms on the corners, but they're not all the way in. They're only part of the way in, right? So what fraction of them is inside the cube? It's 1/8. 1/8 of that atom is inside, so it's going to be times 1/8. And then you've got 6 faces, but those are now half in and half out because they're centered right on the face. So that's going to be multiplied by 1/2. So this gives you 1 plus 3, gives you 4 atoms per unit cell, right? Let me see how to do this. Now note that these atoms, whether they're on the corner or the face, are the exact same atom, right? And in fact, those are the same type of position because I could redraw this structure like so, right? Let's say that we have atoms. Here's our corner atoms. We're looking right along the side of a couple of these unit cells. You've got them on the centers and the corners, right? So you could draw your lattices like this and fill all space, right? That's one way to do it. But you could also, a totally equivalent way of thinking of this structure is to draw a lattice from the centers. Because then what used to be a quarter now becomes a center. Does that make sense? It means that those are 2 equivalent positions. They're no different from one another. Okay? You could have chosen your axes either way. Any questions on that? No? Okay, let's keep going. Next thing we want to cover is what's called the atomic packing factor. And this is a measure of how close packed or condensed the structure is. And it's straightforward. You simply take the volume of the atoms per unit cell and divide it by the volume of the unit cell. So we're going to do this clicker activity together. What is the atomic packing factor for face-centered cubic? And to do this, to make this work, you're going to need to use this expression that we figured out before, which was that A is equal to 4 times the radii divided by square root of 2. If you remember that, and you remember that the volume of a sphere, because we're going to model our atoms as spheres, is equal to 4/3 pi r cubed. So with that in mind, go ahead and calculate what should be the percentage, and you're going to give the answer, I think, in percent. Don't use the percent sign, but if you think it's like 90%, just type in 90, for example. So go ahead and calculate what should be the atomic packing factor for the FCC lattice. How densely packed are we talking about? How much empty space is in there? How much filled space is in there? Remember the volume of the cube, you know how to calculate the volume of a cube. It's just that side length. And you know how to write the side length in terms of r. So your r's are all going to cancel out and you'll just get a number. If you need help, feel free to raise your hand. We've got some TAs. Okay, another few seconds. If you need to phone a friend, do so. Okay, we're going to wrap up the polling on this one. Get your answers in. Okay, we're going to end the poll. Okay, the answer is 74. So 74% this is correct. These are correct. This one's just off. You need to turn it into a percent. So where did this come from? Again, the volume of atoms, there's 4 atoms we just decided. So 4 atoms multiplied by the volume of atom, which is 4/3 pi r cubed. Divide this by the volume of the unit cell, which would be a cubed. But we know what A is in terms of R, so let's rewrite this instead and say that it's equal to 4R over root 2 cubed. When you do this, your R's are going to cancel out, right? So you don't have to worry about that. And you'll end up with 0.74. Multiplying that by 100%, you know that 74% of the space inside this cube is occupied by atoms. And this is as dense as you can get with atoms of all the same size. If you're trying to take marbles that are all the same size, there's no way that you can pack them any closer. If you meticulously place each single marble and try and fill space, you'll never do better than 74%, right? Any questions on this? Okay, well, let's keep going. Okay, next question is, what is the coordination number of FCC atoms? So coordination number, we haven't talked about it yet. Coordination number is the number of nearest neighbors of equal distance. So in this room, this is a square lattice. It's only a two-dimensional lattice in students. It's not three-dimensional. So in a square lattice, if Ryan is our student, right, we want to figure out what's Ryan's coordination number. How many neighbors do you have of equal distance, nearest equal distance? You've got 4. You've got Nicole and Cody, and then you've got Ryan and I don't actually know exactly. What's your name? Behind me. He has 4, right? If this is a three-dimensional lattice, we'd say that he has 6 neighbors, right? 1 more above and 1 more below, right? So now the question is, in a face-centered cubic lattice, how many neighbors do you have, right? So again, let me sketch it one more time. A face-centered cubic lattice, how many neighbors of equal closest distance do you have? You have atoms here on the corners, and you've got atoms on the faces, back, front, side, bottom, top, right? And then remember, you've got other lattices next to it, right? And you could draw the same thing there. You've got other atoms above and below. So what is the coordination number for FCC atoms? Is it 4, 6, 8, or 12? Okay, another 20 seconds. Get your answers in. Okay, get your answers in. 4, 6, 8, or 12. We're going to end it. Okay, ending. How many is it? 4, 6, 8, or 12? People think it is 12. 2/3 of people got this correct. It is 12. Now, where does that come from? Take this blue atom that's on the side of the dice there, right? That blue atom, its nearest neighbor is half of a face diagonal away, right? We could clearly see that, like, there's that distance. That's the distance to its nearest neighbor. Well, that is the same as the distance to that face on the back, to that one on the front, to this one on the neighbor over, right? So in each dimension of each of these planes, the X, the Y, and the Z plane, you've got 4 nearest neighbors, right? On the flat plane, you've got these 4. 1, 2, 3, 4. And then in the vertical plane, you've got 1, 2, 3, 4. And then in the horizontal plane, flat with the screen, you've got 1, 2, 3, 4. So it's actually surrounded by 12 atoms. A coordination number of 12 is an enormous coordination number. That's exceptionally high. Most things don't have a coordination number that. But the reason it does have this is because this is what's called a close packed metal structure. The atoms are just packed together as close as they can. So the coordination number is going to be 12. Right? Now let's think about what would it be for a body-centered cubic. This is our next type of crystal structure we haven't talked about yet. So let's draw it up. In a body-centered cubic, you've got your cubic lattice to start with. You've got atoms on the corners as before. But now you've got one atom in the very center. That's not centered on a face, that's centered within the body, so it's completely inside. So, first off, how many atoms are there per unit cell? Yeah, atoms per cell. There's going to be 8 times 1/8, just like before. That's from the corners. Plus 1 that's completely inside. We've got 2. 2 atoms per unit cell, right? Now, what would be the coordination number? Let's see. Actually, let's do the atomic packing fraction. That's our next question. What would be the atomic packing fraction for this? Actually, before we do it, let's figure out what the ratio is. Yeah, sorry. Before we do that, where would, again, the way I've drawn this, they're really spaced out. In a real metal, they're going to collapse together. Where will they touch in this model? Where will they touch in this model if you collapse it down? Anybody want to take a guess? Yeah, Rob, what do you think?
Weird thing to think about. 2/3 of, or like, I guess 1/3 of the way from one corner to the opposite corner.
Good guess. You're super close. It's actually a quarter of the way across. So let me make sure I've got this right. You're talking about, when you say corner to corner, we're talking about like all the way across the cube corner,
Yes.
like that.
One quarter.
They're going to touch 1/4 of the way along that line, right? If you drew this together, the corner and the center atom will touch, and they're going to touch 1/4 of the way across. So let's draw that. Again, the slice of the atom, if we drew, let me redraw this. Let me draw the slice that cuts this cube in half like that. So I'm drawing this plane, right? That plane, that's represented here. The side length is going to be A, and since this side is a face diagonal, we know that that's √2 times A from Pythagoras' theorem. So now what we want to know is what's the length of this line that cuts corner to corner on that? And again, if you apply Pythagoras' theorem again, that's going to be √3 to A, right? Now if we insert our atoms in this structure, you're going to have an atom right there, and you're going to have atoms here at the corners. Okay? So the entire length of that diagonal line is going to be 4 ionic radii, or atomic radii, and that's equal to √3 times A. So now we can say √3A equals 4R. In the case of face-centered cubic, it was √2A equals 4R. Now it's slightly different. And with that information, now understanding how to write the lattice parameter in terms of R, let's go back to our question. The question was, what is the atomic packing fraction in BCC? Again, what's the volume of atoms divided by the volume of the cube? The volume of the atoms hasn't changed. It's still 4/3 pi r cubed for each atom, and there's 2 of them. Now you're going to divide that by A cubed, but A, the expression for A as a function of R has now changed a little bit. Let me get you started on this one. Okay, so go ahead and finish that one up. You know how to write A in terms of R, so calculate what the packing fraction should be for body-centered cubic. Again, if you calculate the number and it's a percentage, multiply that by 100. Sorry, if it's a fraction, multiply by 100 to turn it into a percentage, and then I just want that number. If you think it's 50%, just type in 50.
AP at always listed as a percentage or decimal.
You can do it either way. Almost, it's usually a percentage. Okay, get your answers in. Another 30 seconds.
We'll come back to that. It has something called the base. We'll come back. It's useful for other things.
Okay, answers in. Our atomic packing fraction for body center cubic is 68%, so yeah, mostly correct there. Again, the only thing to note is recall that now A is equal to 4R over root 3, not root 2 in this structure, because they touch in a different spot than in the face-centered. So this is less closely packed, right? This is still a close packed structure, but it's 68%, say, filled with atoms instead of 74, so it's less so. Question? Sure, yeah, let me plug that in here. So you've got 4R over root 3 cubed. Let's do all the steps, actually. So this is now going to be, so that'll be 8/3 pi r cubed over 4 cubed. So 4 times 4 times 4, right? R cubed over 3. So the 3's are going to cancel. Did I mess up? Oh, that's not right. Sorry about that. That's going to be 9, isn't it? 9. So it's 3 times square root of 3, my bad. 3 times square root of 3. Okay? When I simplify that, I'm just going to punch in my calculator. 8 divided by 3 times pi. The r cubed are clearly going to cancel out. This is now divided by 4 cubed divided by 3 square root of 3. And I come up with that is equal to 0.680175. Right? Or in other words, it's 68% dense. Okay? Okay, we are at, so next class we'll pick up and talk about hexagonal close packed and get to theoretical density.